Hey guys, we're doing section 5.4 today, exponential functions, talking about differentiation and integration together. You'll notice that last time we talked about inverse functions, but you'll notice that if we discussed last time, there was one type of function whose inverse we did not discuss that had recently been talked about. We had talked about, algebraic functions, polynomials. We talked about how to find their inverses. We talked about even things like rational functions and how to find their inverses. There were two types that we skipped, and you can guess what the next couple sections are about. We skipped exponential functions, which have to deal with the natural logarithm, and we also skipped functions involving trig, mainly because the inverses that we're going to talk about are going to be the end of this chapter. So let's go ahead and get started. Section 5.4. Your homework assignment, page 358/382, 1 through 15 odds, 36 through 67 every other odd, and 99 through 123 every other odd. Okay, let's get started. First, let's talk about the magical letter E. E is defined as Euler's number. It was represented by a guy named Leonhard Euler. He was famous for a lot of his work in calculus once it was created, and it lends his name to a lot of different stuff, but E is one of his more well-known and kind of more famous things that he's done. The idea of the natural exponent, e to the x power. Keep in mind, at its most basic level, what this means is e is a number multiplied out x number of times. So if I had, for example, have e to the second power, I'd have e times e, or e twice. If I had e to the fifth power, this would just be e 5 times. So e to the second would be e times e. E to the fifth would be e times e times e times e times e. So e to the x power just means e to some unknown value. Now, the definition, according to our textbook, of the natural logarithm and its inverse is defined as follows. If f of x is equal to the natural log of x, then f inverse of x is equal to e to the x power, where e is referred to as the natural exponential function. So ln, remember, was referred to as the natural logarithmic function. E to the x is referred to as the natural exponential function. So, in other words, ln of x is our f of x, then f inverse is our e to the x, and it also works backwards. So the inverse of e to the x would be ln of x. And furthermore, the big complication, if you have a natural log of e inside of it, it's going to equal x. Because remember, the definition of an inverse is that if you apply one to the other, x pops out. And it works both ways. E of the natural log of x is also equal to x. In other words, e and ln are seen to cancel. Similar to like square root and a power of 2. Those are naturally canceling functions. If I have a square inside a square root, they cancel. If I have an e inside an ln, they cancel. If I have an ln inside of an e, they cancel. Notice that just like with the square root function, how if you have something like the square root of x squared equals x, but if you have square root of something like x squared plus 1, this doesn't work. Same with the natural logarithmic function. They're not designed to work that way. So, this is that idea of an inverse relationship as dictated in our textbook, right here. Boom. They're naturally canceling functions. Because they're inverses, they have to cancel. Now, in case you're wondering, e is designated as a value. I believe it's 0.27178. And you can use e in a calculator just like anything else, just like you can use natural log. So one of the first things we need to talk about here is how to use e to solve an equation. So let's take a look at this first example. I wanted to use a couple of the book examples this time because I think they're pretty good. and there's not very many good homework questions that go through this. So we'll deal with the homework questions afterwards. So it says to solve 7 equals e to the x plus 1. So whenever we see the word solve in a problem, remember that it just means get the variable by itself. So it says solve by itself, it just means solve for the variable. If it says solve for x, it means get x by itself. If it says solve for y, it means get y by itself. So what this question is saying is get x by itself. Well, how do we do that? It turns out you can natural log and exponential both sides of an equation, just like how you can add and subtract to both sides, just like how you can multiply and divide to both sides. So my first step is I'm going to natural log both sides. So I'm going to do ln of 7 and ln of e to the x plus 1. You can do this because the natural log function is a function. Just like anything else, you can do it to both sides. Now, the nice thing is, when I do it this way, because of the canceling properties, ln and e are going to drop, leaving me with just x plus 1 on this side. ln of 7, remember natural log is an operation, just like squaring or square rooting, and then 7 is just inside of it. So this is like the natural log of 7 is like the square root of 7. It's just a number. If I want to solve, I want to make sure to get x by itself. Currently it's not by itself, so I'm going to subtract 1 from both sides. X equals the natural log of 7. Subtract minus 1. And remember, this is outside, so this would be like the natural log of 7 minus 1. And this is considered an acceptable answer. You have natural log of 7, which is a number, and then subtracting 1 from both sides. That's a number. So you have a number minus a number. This is considered to be an acceptable answer. If you don't have a calculator, that's as far as you need to take it. If you do have a calculator, you can actually plug that in, and as you can see in the text, they got the answer of 0.946, which means that a natural log and an exponential function have their own uses outside of calculus, meaning you can multiply, divide, add, and subtract and get through these problems using a natural logarithm, same as you can with an exponential. And of course, if you can do it one way, you can do it another way. So in this example, we're going to, instead of using a natural log to get rid of e, we're going to use e to get rid of a natural log. So here's our equation. ln of 2x minus 3 equals 5. And what this means is we have a function that we're going to need to solve for x. So as like before, we're going to start, first step, we're going to e both sides of an equation, which is allowed. So I can take e to the natural log of 2x minus 3 and e to the 5th, basically turning each side into its own exponential. So if I can add and subtract, multiply, and divide, I can e both sides, I can ln both sides. But however, just like before, the nice thing is e's and ln's are natural opposites. They will cancel, leaving 2x minus 3 on this side. And remember, e is a number, 5 is a power, and a number to a power is just a number. So we can leave it just like that. I could then solve with standard algebraic operations, adding 3 to both sides. And then divide both sides by 2. If you have no calculator with you, that's an acceptable answer. If not, you can actually plug that in and get a solution, which is 75.707 as described. So you can use these to solve basic algebraic operations and use them to cancel each other out in a problem. If you see a natural log in a problem, you can use an e to potentially eliminate it. If you see an e in a problem, you can use a natural log to eliminate it. Notice that for both these, the e was by itself already, which makes doing this process much easier. Just like with the square root function, it's often better to spend time isolating something rather than trying to figure out all the components beforehand. Now let's get into the meat of today. How do we get this in terms of calculus? So let's talk about some algebraic properties and operations that e can do. Theorem 510. It states that for any number a and b that are real, So let a and b be real numbers. Then, first thing that's true, e of a times e of b is equal to e of a plus b. Second thing, very similar. E to the a power divided by e to the b power is equal to e to the a minus b. There's actually a pretty simple way to prove this. You can actually use this same property that we did up here, where we natural log both sides, and it works. It just does. This mainly has to do with the fact that anytime you talk about a natural log, it has to follow all of its properties. And so whenever you look at a natural logarithm, one of the best ways you can do that is by factoring different properties out. There's a great proof of this one, actually right below, which is pretty neat. And then the other one, of course, follows from it. Now, besides that, we have a list of properties. Now, included in this, or should I say not included in this, is the graph next to it. I think the graph is actually one of the more important things you can see. So let's talk about the properties, and then let's talk about the graph. One at a time. One, the domain of e to the x is from negative infinity to infinity, and the range of e to the x is from 0 to infinity. First big detail. Next, it is continuous, increasing, and one-to-one. Now, fun fact, this has to be true because it's the inverse. Remember, one of the properties of inverses is that if the original function is increasing, then the inverse will be increasing. If the original function has something like a is continuous, then this one will be continuous. If the original function is one-to-one, then this one will be one-to-one. Like, it's one of those things. Like, it needs to fit this category. Okay, number 3. And this is a very interesting one. The graph of e to the x is always concave up. Okay? Now, these two properties tell us something about the calculus of this. If we take the derivative, this would tell me it's always going to be positive because it's increasing. If we take the second derivative, this would tell me it would also be positive because it is always concave up. Remember, increasing and concavity are based upon the first and second derivatives, respectively. Number 4, some limit properties from chapter 1. Limit as x approaches negative infinity of e to the x is equal to 0. And limit as x approaches positive infinity of e to the x is infinity. In other words, this is describing the end behavior. So now let's take all these properties. Let's look at what a graph of e to the x actually looks like. Examples in your text, but let's explain some features about this. Okay, first thing, it will have a y-intercept at 0, 1. As we go to the left, according to this limit, it's going to tend towards 0. As we go to the right, it's going to tend towards infinity. Because it's an exponential, it's going to go there very quickly. And one of the other points that's really important here is this point right here, which is at the point 1e. Which honestly makes sense, because if we look at the original equation, we plugged in 1. Plugging in 1, we get e to the first power, which would be just e by itself. And so in this graph, you can see all these different properties listed out. This is the function. If I plug in 0, what that would mean, it would be e to the 0 power, and anything with the 0 power is always, of course, 1. Its domain is from negative infinity to positive infinity, because as we go farther to the left, there's always values, there's no holes, there's no asymptotes. We go to the right, yes, it is going upwards, but it is still existing, so that means the domain is all real numbers. The range, There is a gap in between the axis and this line. So that gap indicates that we do not quite reach 0, but we do get close to 0. And then, of course, we go upwards, which means we're going towards infinity. It is continuous because there's no asymptotes, no holes. It's increasing because over time we continue to go up. And it is 1-to-1 because it passes the horizontal line test. And last little piece here is e to the x is always concave up. Oh, anywhere in here, it is like a bowl, which means it's opening upwards, which means it is concave up. So each of these components allows us to talk about what it is to be an exponential function. Okay. The actual learning today is relatively short. We have only a couple of theorems to talk about besides the basic definitions. What's going to take a lot of time is integrating all these theorems in with previous material. So let's talk about theorem 511, 512, back to back, and then we'll just focus the rest of the time on working through problems. So, theorem 511. Theorem 511 is referred to as a derivative of the natural exponential function. So this is taking a derivative of e to the x. The reason e to the x is such a unique function, not only is it an inverse, not only does it meet all these interesting properties, but, and this is the big one here, but the derivative of e to the x is just e to the x. Meaning a couple things, and this is where we have to really remember our terminology. The derivative means to find the slope generating function, meaning the slope generating function of the exponential function is itself. The slope of the function is the same as the function itself, which is very unique. There's no other functions that do this. In other words, if I want to find a specific value, like let's say what's the slope at 3, I could basically just plug in 3 and get the answer. If I want to find the slope at 5, I could plug in 5 and it's just e to the 5th power. Meaning the slope generating function and the original function are the same. This is the only function that does this, which is why e to the x is so unique. Second thing, well, obviously we're not just going to be dealing with e to the x. Well, if we have a function u, where u in this case is its own function involving x, then the derivative would be e to the u times du dx, or e to the u times u prime. So this is a basic application of the chain rule, and that's theorem 511. So as you can see, these derivatives are in many cases some of the easiest to do because they end up having the same function. But because it's different than everything else, that actually makes it harder sometimes. Because unlike where we have a formula that constantly generates the answer, we just have to use the original function a lot, which can be interesting. Okay, now let's talk about theorem 512. This is the integration of these functions. Like I said, we'll go back and go through each of these, but here we go. The integral of e to the x dx is, of course, equal to e to the x plus c, which again, according to our terminology, means the area below e to the x is equal to e to the x. So the area generating function is equivalent to its original function. This is what makes e to the x so unique and why it has its own separate section in this chapter. It's because it has this unique property. Secondary part, of course, is, don't forget it's plus c. I always forget to say that. The integral of e to the u du is equal to e to the u plus c. So we may end up having to do some u substitutions to get this to work, which is not entirely uncommon. So let's talk through homework problems. My goal with the rest of the time is to get you used to using these functions and the integrations and derivatives of them, to get used to them. And to do so, I want to go through 9 problems. Let's list them out. Our problems are number 40, number 46, number 52, number 62. Notice that I'm focusing primarily on the second part of your homework. That is because the first part just deals with using the properties, and in my opinion, excuse me, it is significantly easier than everything else. And then, of course, 100, 108, 114, 118, and 120. Okay, let's go to some homework problems. And so the first few problems are just using the properties. If you can solve something algebraically, all you have to do is get e by itself and then use an ln to get rid of it, or get the ln by itself and use an e to get rid of it. These first few problems should be pretty straightforward. The fun ones are going to be these: finding the derivatives and then finding tangent lines, or finding the integrals or using definite integrals to verify your results. So let's look at the fun, shall we? Let's start with number 40. Number 40 states we have y equals e negative fifth power of x. Okay, we want to find y prime. Well, in this case, we can use a basic chain rule, which involves theorem 511, part 2. So, theorem 511, part 2 states, if we want to find the derivative of this function, we're going to keep the inner function the same and then multiply the derivative of the power. So in this case, e to the negative 5x would be e to the negative 5x times negative 5x prime, which of course, we all know the derivative of negative 5x is negative 5, which means y prime would be negative 5 e to the negative 5x. Pretty straightforward stuff. Like these integrals, in my opinion, and derivatives are some of the best ones to do. But that doesn't mean they don't have some weird quirks to them, because while the basic ones are nice, as you can see as we go forward, we're going to have more and more complex ones that are going to involve more and more rules from previous sections. So we're going to be forced to use an e that has a product in it, or a quotient in it. We're going to be forced to look at a function that's going to have, an e being multiplied to something, so we're going to have to do a product rule, or an e being divided by something, so we're going to have to do a quotient rule. But anywhere there's an e, we're going to follow the e rules, which remember are theorem 511. So let's now look at 46. 46 states we have y equals x e to the x. Okay, let's do this. So x e to the x. So this is a product, obviously. So if I want to find y prime, let's see, for this one, let's make sure to keep track of my notes here. We used a chain rule along with 511 part 2. For this one, I'm going to use a product rule. Now, when I use the product rule, I have to do left d right plus right d left. So left d right plus right d left. Notice that I'm going back and using my old annotation because I want to make sure to reiterate the points and make sure we all agree where this next line comes from. So we have y prime equals x is just x. The derivative of e to the x is, of course, e to the x, theorem 511 part 1. Plus e to the x is e to the x. Derivative of x is just 1. And so y prime would be the simplified version of this. X times e to the x is x e to the x. E to the x times 1 is just e to the x. This is one variation on the answer. Although, of course, if you want to get really fancy, you could factor an e to the x out, just like how you can factor anything out, and get this answer as well. Both are acceptable. If the question just says find the derivative, we did. That's number 46. So, we're going to be now asked and tasked with doing derivatives and integration using e to the x inside the function. So the basic ones are going to involve the ones where you just have to do it with something like chain rule. The more advanced ones are going to be where e to the x is a part of the function. And so we have to take a look at that piece. Let's now look at 52. Okay, 52 states we have y equals natural log of 1 plus e to the x over 1 minus e to the x. Okay, let's find y prime. Now, for this problem, there are two components to it. We're going to have a chain rule for inside this natural log. And then what's inside the natural log is, of course, a quotient. So there's going to be two pieces to this problem. The first piece is going to successfully take the derivative of the natural log, which is what we talked about last time, or 2 times ago. And the second piece is going to be taking the derivative of this quotient. So let's do one piece at a time. I'm going to do the derivative of ln. The derivative of the natural log is always 1 divided by whatever's inside. So for this one, that would be 1 plus e to the x divided by 1 minus e to the x. This is the derivative of the natural log. However, we must remember to multiply, because it's a chain, by the derivative of the inside, which is a quotient. Now, this quotient has something on top and something on bottom. Let's remind ourselves of the quotient rule. The quotient rule states, again, as we discussed before, low d high minus high d low over the square of what's below. Let's do it. Low, 1 minus e to the x. D high, which would be 1 plus e to the x prime. It should be minus high, 1 plus e to the x. D low, which would be 1 minus e to the x prime, over the square of what's below, which would be 1 minus e to the x squared. So I've not simplified anything just yet, just writing out all my components. Now let's simplify some. Y prime is equal to, so I have a fraction here, and if you have a fraction with a fraction on bottom, you can always invert, meaning this becomes 1 minus e to the x on top, 1 plus e to the x on bottom. Now, let's fix inside. 1 minus e to the x is just 1 minus e to the x. The derivative of 1 plus e to the x, well, the derivative of 1 would be 0. The derivative of e to the x would, of course, be e to the x minus 1 plus e to the x is just 1 plus e to the x. The derivative of 1 minus e to the x, well, the derivative of 1 is 0. The negative sign is going to stay, and then e to the x is just e to the x, so negative e to the x power. All over, of course, 1 minus e to the x squared. 52 is looking pretty good so far, but there's some more simplification I'm going to have to do. If the question just says find the derivative, you could, in theory, stop here, but if the question asks to find the derivative, they probably want to see if you can actually go farther. So in this case, I am going to continue. Okay, allow me to make my next steps. So the first piece is pretty well solid, so I'm just going to leave that. 1 minus e to the x on top over 1 plus e to the x on bottom. So that looks the same. Times. Okay, let's see if we can simplify some inside. So I can distribute this e to the x to both pieces and this negative e to the x to both pieces. And some cool things are going to happen here. E to the x times 1 is, of course, e to the x. That'd be a minus. E to the x times e to the x would be e to the 2x. In this case, remember, e to the x times e to the x, that is actually one of our properties, which states that e to the a times e to the b would just be a plus b. So e to the x times e to the x would be e to the x plus x, or e to the 2x. It's a lot of cheating, but those are the properties. Okay, back here, the negative signs are actually going to cancel, meaning these are all going to be positive. E times 1 would be e to the x. E times e to the x would be e to the 2x divided by 1 minus e to the 2x, sorry, e to the x quantity squared. Notice how I can't simplify this one because there's something being added or subtracted inside of it. I'd have to use FOIL in order to simplify it, and I'm not going to. But I can do one more thing real quick. I have a 1 minus e to the x on top, and I have a 1 minus e to the x on bottom. So I can make that change as well. Let's do it. So end up with 1 over 1 plus e to the x. Okay, inside this function, I have e to the x minus e to the 2x plus e to the x plus e to the 2x. We have e to the 2x and negative e to the 2x. Those are going to cancel. Leave me with 2 e to the x's over 1 minus e to the x. And this right here, I am perfectly fine leaving it right there. There's not much farther I want to go with it. Like, in theory, I could, of course, combine these two fractions together. 1 times anything is going to keep it the same. 2 e to the x. And on bottom, I could just leave them separate. 1 plus e to the x times 1 minus e to the x. Both are acceptable answers here. Really, most any space along here is part of it. But if you're like taking an AP exam, if it was a free response question, they'd give you like 8 points out of 10 just to stop here. They'd give you all full 10 to go over here. If it was a multiple choice question, they'd expect you to get all the way to here, because this is the final solution when you fully simplify it. So this is number 52. Notice the process to this. We have to do each step and then just take the rule to get that step finished. The biggest part of this is that there will be occasional times where a rule is going to suddenly appear and need to be used. Like here. If you take e to the x times e to the x, that becomes e to the 2x, because again, that was theorem 510. E to the x times e to the x would become e to the x plus x, or e to the 2x. It's just the definition of theorem 510. Okay. Last one of these is number 62. See if we can fit it on. Okay. 62. So these are involving finding a tangent line. It turns out finding a tangent line is not as bad as it seems. You have to remember that when it comes to finding a tangent line, there's 2 parts to it. You have to first find the slope, and then once you have the slope, you have to plug it into the formula for a line. So let's talk about 62. We have y equals e to the negative 2x plus x squared, and we're looking at the point 2, 1. Well, let's talk about it. Let's talk about y prime first. So y prime, I would take the derivative of this function. Well, the derivative of e is e with no change. However, because this top function is a function, we have to then use the second part of theorem 511, which states that they have to do a chain rule, which means that we take e to the u times u prime. Well, the derivative of this function is negative 2 plus 2x. So it turns out this, remember, is the slope generating function. If it asks for the tangent line, that just means take 2 and plug it in. The 1 is not needed for the slope because the 1's a y value. This function does not contain y anymore. It contains y prime. So we only need to plug in the x value. Well, we have e, this is negative 2 times 2 plus 2 squared times negative 2 plus 2 times 2. Just keep track of all your stuff. Some mental math here is really helpful. Y prime at 2 is equal to, so this would become e, negative 2 times 2 would be negative 4, plus 2 squared is 4. Negative 4 plus 4 would be 0. Okay, negative 2 plus 2 times 2. 2 times 2 would be 4. Negative 2 plus 2, that would be 2. This is e to the 0 times 2. Remember, e to the 0 power is 1 because anything to the 0 power is 1 times 2, which means my slope is 2. So it says to find the tangent line. Remember, to find a tangent line, you need 2 details. You need m and you need a point. And now it turns out we actually have both. We have m equals 2, and we have the point 2, 1. Let's do this. I would do y minus y1 equals m parentheses x minus x1. Remember, to find the tangent line, which is the instructions that stated, I need to find the slope at that point, and I need a point to work with. Well, I found the slope generating function first, then I plugged in that point and got the slope. Now that I have the slope and the point, I can plug in here, and I should be finished. Y minus 1 equals 2 parentheses x minus 2. This is one acceptable answer. Of course, the other acceptable answer is to simplify this. Y minus 1 equals 2x minus 4, which becomes y equals 2x minus 3. And to illustrate my point, I'm now going to open Desmos and showcase that this is in fact the tangent line at that point. Because we haven't done this in a while, and I want to make sure to re-illustrate my points pretty constantly. Okay, let me just take a second. My equation is, oops, let me showcase. Boop. There we go. E to the negative 2x plus x squared. Oops. This needs to be up here. That's my first line. And my second line is 2x minus 3. Look at that. So this one in red here is my e to the negative 2x plus x squared. And then this one is tangent at that point. Remember, tangent just means it represents the slope at that single point, which it does. That's pretty cool. You don't have to check these because, well, my homework never requires that part. But it is good to always check and see what the thing will look like because, well, I want to make sure I get the right answer. Make sure you didn't make any mistakes. So again, on the last parts of those sections, so like numbers like 62, all you have to do is find the slope generating function first, y prime, then plug in to y prime to find the slope, which we did. Once you get the slope, you can plug the slope and the point into our linear function, y minus y1 equals m parentheses x minus x1. And then that is your solution. And of course, you can simplify farther if you choose. I do strongly recommend checking on these ones because there are a few steps to them to make sure you actually get where you're supposed to get. Okay, well, those are done. Well, let's now talk about the integral ones. Because if I can differentiate, I got to be able to integrate as well. Now, the integral ones start on number 99. So let's take a look at those by looking at number 100. Okay, get my textbook. Boom. Line number 100. All right. We have the integral. This is an indefinite integral because there's no bounds of e to the negative x to the fourth times negative 4 x to the third. Now, on this problem, as is common with some of these, make sure you don't confuse the powers with the numbers and the multiplication. This e to the x to the fourth, the x to the fourth is a lot smaller than this x to the third, so I know the negative x to the fourth is a power, whereas this piece is not a power. Now, as you can imagine, this is pretty common when looking at these kinds of functions, is to do things like u substitution. So that's exactly what I'm going to do. I'm going to do a u substitution. The u I'm going to choose to use, remember, when I choose a u, I want to always make sure to use one that is derivative in the problem. And in this case, I notice right away, negative x to the fourth has a derivative that's in the problem. The derivative of x to the fourth would be negative 4x to the third dx. And I notice right away, the reason why I chose that as my piece is because that is right here. So this becomes the integral of e to the u du. Now, according to theorem 512, the integral of e to the u du is equal to e to the u plus c. So, according to theorem 512, this is equal to e to the u plus c. However, I started the problem with x. I should always make sure to end the problem with x. So I'm going to do a substitution again. This time, everywhere there's a u, I replace with negative x to the fourth. This becomes e negative x to the fourth plus c. Now, if I wished, I could verify that this is in fact the correct integral by taking a derivative. If I took the derivative of this function, e stays e, negative x to the fourth stays negative x to the fourth. You would then multiply using the chain rule, theorem 5.11.2, and take a derivative of this top piece. The derivative of the top piece would be negative 4x to the third, negative 4x to the third. The c goes away because it's a constant. I get right back where I started. Like, we've gotten through a lot of these kinds of problems. I hope that step is natural now. Okay. Let's look at 108. 108 is one of my favorites in this section because it's so unique. We have the integral of e to the 2x over 1 plus e to the 2x dx. So once again, I know this doesn't match any of my standard forms, so my first step is going to be, let's find a u sub. What's something whose derivative is in the problem? And it turns out I can see one thing that looks pretty dang close. If I choose u equal to 1 plus e to the 2x, well, the derivative of that would be 2 e to the 2x using the chain rule. Because remember, the 1 is a constant, it would disappear. E to the 2x, the derivative of e is e. 2x would stay 2x. We'd have to multiply by the chain. And that would be derivative of 2x is 2. You'll notice that in this problem, I have e to the 2x. I just don't have the 2. So what I could then do is divide both sides by 2. I would get 1/2 du equals e to the 2x dx. And now I could perform a substitution. I would get the integral of 1 over u times 1/2 du. Remember, the e to the 2x dx is 1/2 du. There's my 1/2 du. And then I would have 1 over u, because remember, u is 1 plus e to the 2x. I can take the 1/2 out. And then from last section, I remember that the integral of 1 over u is just the natural log of the absolute value of u plus c. Just like before, though, I am not allowed to have a function with u in it if I did not start with u, especially because the function started with x. So I perform a resubstitution. Everywhere there used to be a u, I now replace with 1 plus e to the 2x. This is equal to 1/2 ln absolute value 1 plus e to the 2x plus c. Now, a couple things here. First thing to point out. One, we could move the 1/2 to the inside as a power. That's the property of natural logs, but I'm not going to. It's just not necessary. Two, this absolute value doesn't matter for this problem, although it is correct. 1 is a constant that's always positive. E to the 2x, according to our properties, e to the 2x is also always positive, because e to the x is also positive. So e to the 2x would be positive as well. And so a positive number plus a positive number will always be positive. These absolute value signs aren't doing anything. One more thing, ln and e normally cancel, but because of this plus sign, I cannot cancel them. Meaning this is as acceptable an answer as we can get. Let's talk 114. Number 114 states, and this one is probably among one of the more interesting ones, so take a look. We have the integral of e to the 2x plus 2e to the x plus 1 over e to the x dx. Now, if you look at this problem, you might be looking at it and saying, U substitution. I got to find a way to make this work. And it turns out that seems like a good idea, but it is actually super nasty, and I would not recommend it at all. U substitution is always a good approach if you have this property where du is in the problem. Like, we chose this u because du was in there. We chose this u because, well, the du wasn't quite in there. It could be modified quickly enough that it was in there. With this problem, like, what do you choose as your u? Do you choose the denominator? Well, the derivative of e to the x is e to the x, and the top contains e to the 2x, and e to the x, and a 1. Like, it doesn't get any better. Same thing with, like, if I choose the top. Like, the derivative of the top would be 2e to the 2x plus 2e to the x plus 1. It would just, the 1 would disappear, the 2 would stay, a 2 would move out. Like, it doesn't get any better. It just doesn't. So instead, for this problem, I like to remind us of a property of algebra. Any fraction may be rewritten as multiple fractions separated by their operation. And this is allowable. Notice that I can split the top apart, but you can never split the bottom. Now from here, I can actually simplify some. So let's talk about those properties one more time. If I have division of e's, the division of e's means subtract them. So if I have e to the 2x divided by e to the x, this becomes e to the x power. 2x minus x is just x. I have e to the x divided by e to the x. E to the x and e to the x will cancel, leaving just 2. And of course, anything in the denominator can be brought up to the numerator, like so. It turns out that this integral is actually pretty straightforward, if you see it this way. I can now integrate e to the x separate from than if I integrated just 2, and separate from if I integrated e to negative x. Now, let's remind ourselves of some things. This one, integral of e to the x dx, according to theorem 512, is, of course, e to the x. Integral of 2 would become 2x. Integral of e to the negative x would become negative e to the negative x. You do a u substitution here. And then, of course, each of these would have their own c, but we combine all those together. And it turns out this is actually a fine solution. There's no other ways to simplify it. It's good. Notice that for many problems, u substitution is a great approach, but that does not mean it's the only approach, and it does not mean it's the best approach. U substitution on number 114 would make you tear your hair out, and I don't want you going bald too early. Look for other ways. You know, if you find that you're spending a lot of time on a problem and you just aren't getting to a better way, maybe, just maybe, look for a different approach. Okay, we have 2 left, 118, excuse me, which I believe I can fit down below here, and then 120, which is the last one, and it's a fun one. Okay, 118. So these are the definite integrals. So let's take a look at it. We have the integral of 3 to 4 of e to the 3 minus x dx. Okay, for this one, I'm going to use a couple things here. I'm going to do a u substitution, where I'm going to set my u equal to 3 minus x, which means my du is equal to negative dx. I don't have negative dx in the problem, so I can do negative du equals dx. Now I can do a direct substitution. Everywhere I see a dx, I can replace with negative du. Everywhere I see a 3 minus x, I can replace with just u. Let's do it. Integral. This becomes e to the u times negative du. The negative I'm eventually going to pull out front, but not right now. Now, I have the option. I can either leave these in terms of x, which they were originally, or I can convert them into in terms of u. I'm going to choose to convert. If I convert, this becomes 0 because 3 minus 3 would be 0, and this one becomes negative 1 because, again, 3 or minus 4 would become negative 1. Notice they've essentially removed all x's from the problem and therefore finished this problem using just u's. Let's take a couple of steps here. I'm going to move the negative up front. Negative integral 0, negative 1, e to the u du. I could take another step here where I could use a property to switch these around, which is actually what I'm going to do. Remember, if you ever wish to switch the boundaries, all you have to do is negate the entire function, which means this becomes the integral from -1 to 0 of e to the u du. And that's acceptable. Because remember, if I wish to switch the boundaries, I have to negate the function. But if the function is already negative, it's just going to become positive. Now, I can actually integrate. The integral of eu du is, of course, eu plus c. But evaluated from -1 to 0 means we don't need the c. And now I can plug in. I would get e to the 0 power minus e to the negative first power. That's an acceptable answer, but I'm going to simplify just a little bit. E to the 0 power is, of course, 1. E to the negative first power would mean it's just 1 over e, and that's a far better answer. It turns out if you convert back into x's, you'll get this exact same answer, just takes a little bit more work. If you get a calculator out and plug this in, you should get the exact same result, and it turns out that's exactly what happens. If I wish to check my work on this one, which I will do, I'm going to pull up Wolfram Alpha. Typing functions into Wolfram Alpha takes a little bit of practice. So here you go. To type this function in, the original function was the integral of, from 3 to 4 of, and then we just type in the function. The function was e to the 3 minus x dx. It'll attempt to interpret what I've written. I make sure to always check what it says. Notice that I made a mistake. It has 3 minus x when I want both things in the power, so I just put a parentheses around them. There we go. It tells me it is e minus 1 over e, which is 0.6212. If I do mine, which is 1 minus 1 over e, get the same result. 0.63212, 0.63212. They're the exact same. They just combine the fraction in, or two fractions into one, which is, its own thing. So that's 118. This is a u substitution where we have an integration. We'll do number 120 to finish out. That'll be our last problem together, and that'll be it for today. Let's do number 120. Number 120 is, it's interesting. Let's take a look. Number 120. I'm going to zoom in just a little bit. Here we go. It says 120. Integral. Oops, off the page. Integral from -2 to 0 of x squared e to the x cubed over 2. Yeah, dx. No, this is not 3 over 2, it's x cubed over 2. You have to look very carefully at this problem. The 3 is significantly smaller than the 2, and that matters a whole heck of a lot for problems like these, okay? So be very careful. If you aren't very careful, you can have a lot of problems with these ones, so be very careful. Okay, with number 120, you can obviously see that we're going to have a u. U is equal to x cubed over 2. Which means my du is equal to 3 over 2 x squared dx. This is pretty close to what I have in the problem. I have x squared and dx, but not 3/2 x squared dx. So move the 3/2 over and become 2/3 du equals x squared dx. From here, everywhere there's an x squared dx, I can replace with 2/3 du, which gives me this new integral. The integral, x squared dx becomes 2/3 du, and then this becomes e to the u power. In this case, I'm actually going to do the other version where I don't convert, So this is where I have x equals -2 and x equals 0. I think, if I'm honest with you, it is so much easier to just convert. Because going back and replugging back in x, then still having to plug in these numbers is a pain. It's up to you. It really is. It doesn't matter. You get the same result either way. Just try it out a couple times. You'll see what happens. So the 2/3 can pop out. We still have x equals -2. We still have x equals 0 of e to the u du. According to theorem 512 part 2, this 2/3 would pop out front. Integral of e to the u would just be e to the u, evaluated from x equals -2 to x equals 0. We don't have x anymore, so we need to put it back in. So we do 2/3 e to the x cubed over 2, evaluated from x equals -2 to x equals 0, which means we would get 2/3 e to the 0 cubed over 2 minus e to the -2 cubed over 2. Okay, I will simplify this by hand. 0 cubed is 0. Divide that by 2 is still 0, so we end up with e to the 0 power, which you'll remember, e to the 0 power is 1, minus -2 cubed is -8. -8 divided by 2 would be e to the -4th. And this right here is as simplified as I probably want to get. We could, of course, go back and verify the solution. I would recommend it 9 times out of 10. This one, we're getting pretty close to that hour mark, and I'm sure you guys are dying here to enjoy your weekend. So there it is. Reminder, our homework assignment for tonight. Page 358/382. 1 through 15 odds. Those are the ones dealing with just the properties of the exponential function. And the ones that are calculus based are the 36 through 67 every other odd, and 99 through 123 every other odd. I hope you guys have a good rest of the weekend, and I will see you guys on hopefully Monday this time.